morning. In today's class, I will be dealing with monopropellant rockets and hybrid rockets as a continuation of the chemical rockets. But just to make sure we are very clear about what we have done so far, let us quickly review what are the things we learnt in solid propellant rockets and the liquid propellant rockets. See, solid propellant rockets we have gone into detail, but we said controllability is a problem in solid propellant rockets. What do we mean by that? Once a solid propellant rocket gets ignited, like you have, let us say, a star grain or a cylindrical grain, and once this grain is ignited, it is just not possible to stop the combustion. Whereas in a liquid propellant rocket, since you are feeding the propellant from a tank into the combustion chamber, maybe by a pump, maybe by gas pressure, maybe regulated or blow down mode, or any other mode, stage combustion cycle mode, it is always possible to stop feeding it and you can have control. Therefore, we can say a liquid propellant rocket is more versatile in that control is possible, and not only can you control the flow, but supposing I have a control system, like I want to control the chamber pressure, maybe I put some control here, maybe with respect to compare with something else, and therefore using this control system I can control the chamber pressure. I have a reference chamber pressure, I make sure that the reference chamber pressure and this are same. Supposing I want to control the mixture ratio, maybe I monitor through a mass flow meter the mass of fuel which is flowing in, like let us say m dot f, which it measures. I can measure the m dot o, I can instantaneously record the value of m dot f by m dot o through a particular circuit. Let us say I feed this signal over here, I feed this signal over here through a mechanism here, and if I find that the mixture ratio is exceeding, I can give a command to these valves or to a valve upstream to slow down and all that. A control is possible, not only starting and stopping, but also mixture ratio control, maybe pressure control, and hence the thrust control. Therefore, we say a liquid propellant rocket is more versatile. Not only is it more versatile, it also has higher performance compared to solids, because in solids we add aluminum, the molecular mass of the exhaust is high, whereas here if I choose hydrogen oxygen, my performance is, or my specific impulse is, quite large. Therefore, we can say in general the liquid propellant rocket is more versatile, has better performance than solid propellant rockets. But then we also see it becomes a little more complex. I have plumb lines, I have tankages, I have pumps, and therefore it is little more complicated. But I will come back to this. Can we simulate this through theory is something which is questionable, and maybe I will spend some time on it. Therefore, we say liquid propellant rockets are more versatile, and let us take a few examples. Like for instance, when we studied the theory of rocket propulsion, you will recall we said boosters are those rockets which are used during takeoff, and the upper rockets are things which are known as sustainers or upper stage rockets. For booster rockets, we found that in addition to ISP, the term like rho ISP becomes important. You will recall, and why did we say that? The mass of the cases, mass of the upper stages become important, and under those conditions we derived an expression that rather than ISP, the product of the density of the propellants multiplied by ISP becomes a figure of merit of the rocket. Therefore, whenever I choose the booster stages, that means the stages which first start off, it is essential to use what we say is dense propellants. What do we mean by dense propellants? Propellants having higher density. And when I talk in terms of dense propellants, what immediately comes to my mind is, can I use propellants which are something like dense, like let us say UDMH, which has a good density, maybe N2O4 as a oxidizer? Can I use liquid oxygen with kerosene? These are somewhat denser, and therefore we find maybe liquid oxygen kerosene has been traditionally used for the booster stages, and examples which we saw were the F1 engine, which was used for the Apollo rocket, and mind you, this is something like 30-40 years old, and this has a huge thrust of something like 6.8 meganewton. That means 6.8 into 10 to the power 6 Newton, or you are talking of several thousand or million tons of thrust is what we are talking. The chamber pressure of this, which uses liquid oxygen and kerosene, is something like 7 MPa, that is 70 atmospheres. Pressure is low, thrust is large, and the cycle of operation is the gas generator cycle. Another rocket which is also used as a booster is the Russian rocket known as RD-170. The beauty is it has a higher thrust than this, of the order of something like 7.25 meganewton, maybe same class, but the chamber pressure is extremely high, of the order of 24.5 megapascal, that is something like 240 bar as it is. And since it is a high pressure with a large thrust, we use the staged combustion cycle engine. Therefore, these are the two examples of very large rockets which use liquid oxygen and kerosene. One uses the staged combustion cycle, and when you go to lower chamber pressure, you use the gas generator cycle. Maybe some other examples, well, LOX, kerosene, these are the two typical examples. In India we started with UDMH N2O4, and this is what the French used earlier in their Ariane launch vehicles for boosters. But ever since we told that UDMH is cancer causing, it is also costly, the trend is not to use UDMH, and therefore presently the Ariane rocket, like let us say Ariane rockets 1 to 4, they make use of UDMH N2O4, but the more recent one, Ariane 5, does not make use of UDMH N2O4. But what we use is a derivative of what was used in Ariane. It also uses a gas generator cycle, and the typical thrust is around, let us say 60 ton, or let us say 60 ton thrust, and the chamber pressure is of the order of the same value, around 58 to 62 atmosphere pressure, that means 5 to 6 MPa. Well, these are some of the booster engines with let us say the heavy propellants, LOX, kerosene and UDMH N2O4. But what was done more recently is, if you look at the space shuttle, mind you, space shuttle has now performed its job, it is no longer operational, the last space shuttle is over. What was done in space shuttle is, you had liquid hydrogen and liquid oxygen engines. These generate a thrust of around 1.8 meganewton. The chamber pressure is again quite large, something like almost like 19 MPa, that means 190 atmosphere pressure, and this used the staged combustion cycle. See, even though the density of the propellant is small, they have a huge booster, and we have seen pictures on the back of it. You have a liquid hydrogen tank, they carry the liquid hydrogen, and you operate liquid hydrogen, liquid oxygen. You have 3 such engines which are used, and this is used in the space shuttle. Whereas if you use the French type of things, they use, again as I said, the Ariane 5 went off from using UDMH N2O4 to using LH2LO2. They have a thrust of around 1.1 meganewton, that means 1.1 into 10 to the power 6 Newton. The chamber pressure is around 11 MPa, and since the chamber pressure is less, they use the less complicated gas generator cycle, GGC. Therefore, you find different types of propellants are used in different stages, and when we want maybe much less powerful engines, we can even go for gas pressurization and use it as the 4th stage. Maybe you can use MMH and N2O4, and maybe the other propellants like what is used in missiles. These are typically the different type of engines used. We see sometimes gas generator cycle being used, sometimes staged combustion cycle is used. Staged combustion cycle is used only when the chamber pressure is very high, and these give very extremely high performance. Something which we must remember, and I told you of an engine known as RL10 engine, which we said uses liquid hydrogen, liquid oxygen, but uses the liquid hydrogen in an expander cycle. What was an expander cycle? One in which the hydrogen gets evaporated while cooling the chamber, and that vapor of hydrogen is used in running a turbine. This is very powerful. The chamber pressure is low, of the order of 3 to 4 Pascal, that is 30 to 40 atmosphere, and this has been extensively used in many missions for the upper stages. Of late French people are working, and that is challenging, in a particular rocket known as a Vinci rocket. I give a homework problem on Vinci rocket. This again uses the expander cycle. In fact, I ask you to calculate what must be the heat transfer from the chamber to the coolant in order to have an expander cycle. This Vinci rocket has a turbine which rotates, I told you, around 1 lakh RPM. Therefore, these are some of the developments. Maybe we should keep some of these things in mind as we study the liquid propellant rockets, right. And it is quite challenging. We find Vinci being developed, we find other rockets being developed, but something else with respect to liquid propellant rockets compared to solid propellant rockets is it is easily amenable to a theoretical analysis. Not that I am telling that it is superior in any way. See, a solid propellant rocket has distinct advantages. Supposing I want a short takeoff and landing for an aircraft, I can just have unrestricted burning, attach 1 or 2 rockets beneath my wings, and then just burn it. It will give me thrust immediately for a few seconds or a second, and I can take off my aircraft in a very short runway, as is necessary in the forward areas or in some military aircrafts. So we also call it as rocket assisted takeoff. The short takeoff and landing, which uses rockets, is also known as rocket assisted takeoff. This is possible with solids, but what I wanted to say was, let us not say everything is liquid, but when we studied liquid rockets, we never really studied about liquid rocket. A description of rocket is like this. All what we studied is, we have a tank, propellant flows in pipelines. If it is a pump, I know pressure is increased in a pump. I supply it to the injector. What does the injector do? It sprays it into the combustion chamber. The thing evaporates and burns. Well, everything we have studied in other subjects, fluid flow, maybe thermodynamics of generation. Therefore, we can say, well, a theoretical analysis of a liquid propellant rocket for, let us say, steady performance prediction, or let us say transient performance, or if we say performance, or even if you say I want to look at the dynamics of it. Maybe if I were to put some shock into one of the systems, how is the rocket going to respond? Something like dynamic response is all possible, and this is where some attention is required, and there are several people working in these areas at present. Let us quickly go through what I mean by this and how do we do it. Supposing we have a liquid propellant rocket, what did we have? We have the tank cages, and from the tank cages what have happened? I just draw a single tank cage. From the tank cage through the plumb lines, maybe curve and all that, through these lines propellant flows. And how do you establish the pressure? If the tank pressure is, let us say, PT, how do I get the pressure here? I get a drop in pressure, and I say that the drop in pressure goes as maybe 4 FL over D into V squared by 2, maybe under some conditions, but I need this. Therefore, I can write this equation as pressure drop in a pipeline goes as something like a resistance into velocity goes as the mass flow rate, let us say m dot square of the propellants. But under dynamical conditions, I have the mass of propellant which accelerates. That means I have mass into acceleration, or rather I have mass into dV by dt. And what is the mass? Rho AV. Therefore, I am talking in terms of something like dm by dt, and therefore, because of this acceleration, I have acceleration taking place, I have a pressure drop taking place, I have a force due to acceleration, which is the Newton's second law, and therefore I can say the delta P due to acceleration I can write as something like an inductance, or let us say some value of inductance, like we have current changing into dm by dt over here, dm dot by dt, because what is it, I have dv by dt, and therefore I can write the net pressure drop under dynamical conditions. I can write it as something like L into dm dot by dt is the pressure drop in a line. This is under static conditions, this is under dynamical conditions. Therefore, this is the total pressure drop. How do I get the pressure rise in a pump? Let us say this feeds into a pump, let us say, and what does the pump do? It increases the pressure from a small value to a larger value, and here you get the outlet. And how do you get the pressure in a pump? We had said pressure in a pump, delta P across a pump, let us say, is equal to the flow rate, which is equal to Q, or is equal to m dot, into something like delta P. But let us be very clear, from unit point of view it should be Q dot, or rather it should be m dot by P divided by density is the rate of work done in a pump. And similarly, the pressure drop in a turbine which drives this pump is given by the work done in the turbine, which is, after all I am taking from gas generator a gas and driving the turbine as it were here. What was it equal to? We said mass of the gas generator into Cp into Tgg into 1 minus 1 over the expansion ratio in the turbine into gamma minus 1 by gamma, right. This was under steady conditions. Well, I can also figure out, therefore I know the pressure here, I can find out the pressure here, I go all these lines, get into the injector, I can find out the mass flow rate through the injector. Therefore, everything is possible to be calculated from simple equations. Let us go one step further. We also tell, well, I know the pressure drop across a pump, pressure rise across a pump, the pressure drop across a turbine, and supposing I want the delta P across a pump, it depends, we saw on non-dimensionalization, depends on the speed, depends on the mass flow rate, depends on the density, or Q and rho, or rather I can write this as equal to, I can write this as, let us say, some constant k into n square plus k2 into n into the mass flow rate plus k3 into m dot square, and this can be proven considering the blade geometry and all that, that the pressure rise across a pump is given by this particular expression. And we also told ourselves that across a turbine, and all turbines were impulse turbines, and this could be written as the resistance into m dot square. Therefore, I know the pressure rise across a pump could be written in terms of the speed of the pump and some constants over here. Similarly, the pressure drop across a turbine can be written like this. We already had the expressions for power of a pump and power of a turbine over here. And how do I use the power of a pump and power of a turbine? Let me put it in terms of capital P. I can translate the power into a torque. Torque of a pump is equal to power of a pump divided by the angular rotation. This is tau of P. Tau of a turbine is equal to power of a turbine divided by omega. And what is happening is the turbine drives my several pumps, maybe fuel pump, maybe the oxidizer pump, and therefore I can say that torque from a turbine minus torque from a pump should be equal to the moment of inertia of the moving parts, which can always be calculated, into d omega by dt. And therefore, I know all the things, I can now use all these sets of equations put together to be able to find out the pressure at each of the points, to be able to find the speed of the turbine, and not only the speed of the turbine, but I will be able to find out as a function of time how the speed of the pump should develop, how the pressure should develop, and what do I use to get the pressure? I have a gas generator, and what is the equation to the gas generator which we wrote earlier? We said dm by dt is equal to mass which flows in minus mass which flows out. Mass which flows in was equal to, we know what is the mass which is flowing, the mixture ratio, what is flowing. Mass which flows out is equal to 1 over C star into P into AT, and what is dm by dt? Dm by dt was equal to dP by dt into PV by RT is equal to m. Therefore, we have m is equal to PV by RT, V is a constant, therefore, V by RT is equal to m dot n. And how do you get m dot n? We said from the injector you have CD into area of orifices into something like 2 rho into the injection pressure minus the pressure in the chamber. Therefore, I know what is the thing which is flowing. Therefore, I am able to get all what I want through a set of equations which describe my system, and it will be indeed challenging to be able to put together all these things with dynamics, and this is what all of us like to do with liquid propellant rockets. This we can say is something like a dynamical simulation or a theoretical simulation of a liquid propellant rocket. And you will see people always talking in terms of, do you have a dynamical model of your system or do you have a static model of the system? All what is meant is these equations have to be put together. Maybe I went through it hurriedly because we have covered individual components together and there is not much point in again repeating the whole thing, but I think we should keep this in mind. And in a dynamical model, not only you solve for the parameters at the different places, but also you put your control system. And what is the control system? You would like the mixture ratio to be fixed and in the chamber. For the mixture ratio to be fixed, you need to have something control system which controls this as it is moving. I think this is all about the liquid propellant rockets, and you see even a simulation is possible. Having said that, we continue with our exercise into maybe monopropellant rockets. And what are monopropellant rockets? We use a single propellant. You know, when I use a single propellant, how does it break? How does it generate hot gases? See, when we were in our high school, we talked in terms of certain substances known as catalysts. A catalyst is a substance which improves the rate of a reaction without itself taking part in the reaction. That means it does not get changed during the reaction, and a typical reaction is if I have CO plus O2, I want to form CO2, dry CO and O2 will not form this, but water vapor will catalyze the reaction and help you to get it. You have catalysts which could either be homogeneous or it could be heterogeneous. Let us take an example. By heterogeneous means it is in a different phase from what is the substance which it is catalyzing. And why does it have to happen? Maybe this is your reactant, maybe some substance like let us say a single propellant over here. Combustion products have much lower energy level. This is the heat of formation or the energy here, this is of the products over here. I have to give some energy for it to start reacting, and once it comes here it goes this, therefore this axis becomes the progress of the reaction, and this becomes let us say the energy involved. Well, this is the ignition energy required to start a reaction, and once a reaction starts the reactants go to products. When I use a catalyst, I sort of reduce the type of energy which is required. That means a catalyst reduces the activation energy to start a reaction. That is the basic function of a catalyst. And we have certain substances like let us say silver. Silver, when I have a silver wire, make it into a mesh and I pour hydrogen peroxide over it, the hydrogen peroxide dissociates into H2O plus O2, maybe 2H2O, 2H2O plus O2. And similarly, the silver is heterogeneous because it is a solid, it catalyzes a liquid hydrogen peroxide into two gases, steam and oxygen. Similarly, if I have a catalyst like iridium, maybe iridium ion, what it does is when iridium ion is in contact with hydrazine N2H4, it immediately, or when it is the iridium catalyzes the decomposition of hydrogen into ammonia plus whatever is left. Let us say you have 3 N2H4, let us just say is equal to, you have 4 NH3 plus N2 over here, 12 here, 6, 4 plus 2, 6 here. This is the decomposition reaction, and in presence of iridium ion, the hydrazine is decomposed to ammonia and nitrogen. If you look at the heat of formation of hydrazine, which we studied when we were studying propellants, we said it is around plus 50.3. Ammonia, if you look at the heat of formation delta HF star at standard condition, this was something like minus 49 or so, and therefore you say minus of 4 into minus 49 minus of 50.3, that is 3 into 50.3, and this is positive, and therefore the net one contributes to the heat over here. We had minus of heat liberated in the reaction is equal to 4 into minus 49 plus 0 here minus of 3 into 50.3 kilojoule per mole. I had 3 moles of this, I had 4 moles of this, therefore this and this get added over here, plus and plus here, and I get heat of decomposition over here. And this is how a monopropellant rocket works, and therefore a monopropellant rocket will be different from the rockets which we studied so far, in that I just have a chamber. All what I need to do is put catalyst over here. And how do we put this catalyst like iridium? I have balls, I need iridium to be coated, and I take maybe alumina, which is something like a porous refractory. I make balls of aluminum, maybe 1 mm or 2, 3 mm thick or 3 mm in diameter, spherical ones, and into this I coat iridium ions on it. Therefore in depth also it is porous, therefore iridium ions will be there. I put all these things over here, and into this I pass hydrazine. Hydrazine, when it is flowing, will come in contact with iridium, because these are all porous things, and into the alumina I have iridium, it will flow into it, it will react with iridium and decompose, and out of the thing I will get the dissociated products which are at a high temperature. The typical temperature could be between 1800 Kelvin to a lower temperature of 800 Kelvin. I will come back why this temperature changes. Therefore this is the function. Therefore all what I now need is, I have a gas bottle, I have a hydrazine tank. From the hydrazine tank I inject the hydrazine into it, it gets into the catalyst bed, reacts with the iridium in the particles of alumina which is impregnated into it. Like what we do is, we take these alumina Al2O3, it is porous, I put something like hexachloroiridic acid or something and make sure that when I treat it I get iridium which is available on these crystals and inside the pores, and when hydrazine flows it decomposes. This is the function of a monopropellant thruster. But what happens when propellant keeps flowing, the ammonia which is formed begins to again decompose, and what happens is NH3, mind you I formed 4 NH3 here, the 4 NH3 which is being formed here could again decompose into something like 6H2 plus 2N2. In other words, as it begins to react, immediately I get ammonia and whatever nitrogen there, and this ammonia further decomposes because of the high temperature whatever is available here into hydrogen and nitrogen. You find that the heat of formation of hydrogen is 0, nitrogen is 0, ammonia has a heat of formation, we said something like minus 49 or something, minus 49 kilojoules per mole. Therefore you find that this particular reaction, minus of minus, which becomes, again we have 2 minuses here, therefore this reaction becomes endothermic, and therefore it absorbs the heat from the reaction, and therefore this decomposition will rob heat from this particular reaction, and therefore more the dissociation, less will be the temperature, or rather as the dissociation increases, ammonia increases, the temperature will keep on falling. If there is no dissociation, the temperature is around 1820 or 1830 Kelvin, and if the dissociation is complete, I get something like 800 Kelvin. How do I write both these reactions together? If I now say X of the 4NH3 which is formed dissociates, I can combine this equation and then write it as 3 N2H4 is equal to, now I get 4 1 minus X has dissociated, X has dissociated, therefore I am left with NH3, and now what has happened? I get for each which has dissociated, now I get 6XH2, and now I get 2, that means 1 plus 2x, because I had originally N2 of N2 over here. Therefore, this becomes my equation when part of the ammonia which is formed dissociates into hydrogen and nitrogen. And now if I find out the heat of formation as X increases, I find as X increases, the heat liberated comes down, therefore the temperature comes down, and this is where I said temperature decreases from something like 1800 to 800, but I find I am getting more and more of hydrogen. Therefore, my molecular mass of the products X also decreases. This decreases from a value like 19 to something like 10, you can work it out. I give a homework problem on that, and therefore, since molecular mass comes down and temperature comes down, if I were to put both of them together in terms of either C star or in terms of specific impulse, I find my specific impulse with respect to X is maximum for a value around 0.2 dissociation, and therefore my ISP goes like this and keeps decreasing. I get a maximum value around this. The change in specific impulse between 0 dissociation to 0.2 dissociation does not change much, but thereafter it begins to come down. Therefore, you would like to configure your catalyst bed such that you have degree of dissociation as 0.2, and that is when you get your maximum performance. This is the background for monopropellant rockets. Let's try to put things together now and ask ourselves what is required for a monopropellant rocket. Well, it's very extremely simple. I have a tank, I have a pressure regulator. The pressure regulator supplies propellants to a catalyst bed, and this catalyst bed decomposes it and out goes the products through the nozzle. This becomes my catalyst bed. I need an injector, maybe an ordinary shower head injector which forces the liquid on this is okay, but if I force it like this on the thing, it does not uniformly get distributed. Therefore, maybe I could put some screens here, metal screen over here, impinge it on the screen and distribute it uniformly, that is one solution, or else I could allow the bed to be very much near. I put metal screens over here, I inject it as a shower head here, impregnate the catalyst bed right at the injector, and this is one other configuration of doing it. It is of course necessary to make sure that whenever you have put such injectors, could be some screens, could be shower head, could be these metal meshes over here, whatever we put, it is also important that the dribble volume, mind you, we talked in terms of manifold, must be small. If dribble volume is large, it keeps on dribbling and you will have thrust generation with respect to time. Instead of giving like this, it may keep on going for a long time. That is the dribble volume. Well, these are the only things in monopropellant rockets. We find it is quite simple, and in fact it is widely used for in satellites for controlling the trajectory, or let us say orbit control, and for attitude of the satellite. This is where we use it. Having said that, let me quickly run through what I have been telling so far in monopropellant rockets. We talk in terms of a gas bottle, pressure regulator, hydrazine tank, pushes it into the catalyst bed over here. You have a valve, you can stop and close, you can do it in pulses, but if you do in pulses, the catalyst bed gets hot, heat gets transferred back here and it may heat up the injector. If the injector becomes hot, hydrazine may decompose and even cause an explosion. Therefore, what is it you do? You go back and tell myself, well, this is my catalyst bed, this is how I expand it. In order to cool it, I am forcing the hydrazine through it. I put some metal here, just like I use fins in the case of a motorbike. I use fins here such that this part gets heated and heat gets radiated out. This is something like a, we say between the thing here and the monopropellant rocket here, I have something like a standoff. As I told you, I would like my manifold volume, which we called as hold up volume of the propellant, to be as small as possible. I have the injector here, which could be shower head or some of the screens I am talking of, and this is the catalyst bed. How do you specify a catalyst bed? Let us just spend a couple of minutes on the catalyst bed. We told ourselves, well, catalyst bed consists of alumina. In the alumina, I have lot of pores or holes, and when I impregnate it, I make sure the iridium is available at all the places, and therefore, when hydrazine flows, it wets this. That means the alumina is a substance which is permeable to hydrazine, permeable. Therefore, permeability is an important parameter. This is iridium in alumina, and therefore, it must be permeable, and therefore, how do you design a catalyst bed? After all, you have a bed of a certain size and hydrazine flows into it. Therefore, it is specified in terms of mass flow of hydrazine in grams divided by the surface area, that means so much centimeter square, and you are flowing per second, and this is known as bed loading. In other words, what we have to necessarily ensure is that if I have the surface area of this bed to be so much, let us say a meter square or a centimeter square, and if I flow hydrazine at so much grams per second, mass flow rate of hydrazine in grams per second divided by the surface area tells me the bed loading, and this bed loading tells me bed loading and the length of the bed will what tells me whether what amount of dissociation I get of the ammonia. Therefore, this bed loading typically varies between 1 gram per centimeter square second to 50 grams per centimeter square second. For large rockets might be, whenever we use monopropellant, we do not go for high thrust, maybe the maximum thrust which we can go is something like 500 Newton to 1000 Newton. The smallest could be anything small, maybe millinewton or something like that. For very small one, we use a small bed loading. For larger ones, we use a larger bed loading. This is all about the monopropellant rockets. Therefore, I think I should stop here, but or rather let us just finish off. We say that the temperature with the degree of dissociation keeps coming down. The molecular mass also comes down from something like 18 to a value around 12 or so, and when I put both the things together, the C star has a maximum value around 0.2 over here. Well, what are the problem areas in monopropellant thrusters? Well, the catalyst bed runs hot, therefore, the injector runs hot, hydrazine could dissociate, and if hydrazine being a monopropellant, it could as well explode, and therefore, we must ensure we have thermal management. And how do we do the thermal management? We told ourselves, well, I have something like a fin which will dissipate the heat whenever the thing gets hot and remove the heat from here. Well, dribble volume must be small. You know, we have some problems whenever we have catalysts, like for instance, whenever I have these alumina things over here and we said that the thing goes wet set, it could sometimes break, which we call as attrition. What is attrition? You have all these one with the other and all that, it creates some pressure and leads to breakage of the catalyst, and some of the catalyst gets out through the nozzle, that is known as loss of catalyst. And again, we told ourselves when I use in spacecrafts, I need to have something like a positive expulsion system. Maybe the bladder material might get into the hydrazine and might poison the catalyst, that means the activity of the catalyst can come down. Therefore, the two things which we have to keep in mind is whenever we have catalyst, the activity of the catalyst must not get disturbed, because you have hydrazine might contain some aniline, it might contain some material from the bladder which can go and block the iridium and make sure that it does not function as required. Therefore, we must ensure that when the activity of the catalyst is decreased, we call it as catalyst gets poisoned, it is no longer effective, and we must prevent the poisoning of catalysts. And of course, whenever something gets poisoned, it is not able to do its performance well. But the main drawback with using the monopropellant thruster is it has low performance compared to bipropellant rockets. The performance is very much lower, maybe something like 3000 Newton second by kilogram is the ISP of, let us say, a low performing propellant. We called it as propellants which have relatively low energy propellant. Compared to that, this might be around 1500 Newton second by kilogram. And therefore, there has always been an interest to say, supposing I have a monopropellant thruster, that means I have a catalyst bed, I have an injector over here, I have the thruster over here. Can I put some electrical heating and improve the temperature? We said that the maximum temperature is around 1800 Kelvin. I increase the temperature using electrical heating, and such type of thrusters in which I have monopropellant decomposition to an intermediate temperature and still increase the temperature further to improve my ISP is known as augmented electrohydrazine thrusters. I will revisit this problem maybe after some 5 or 6 classes when we talk of electrical propulsion. That means, since the performance of monopropellant thruster is on the low side, I can always improve it by electrically heating the gases from the higher temperature of 1800 to something like, let us say, 2500 or so, and still get my high value of specific impulse. Well, this is all about the monopropellant thrusters, but there are some things which we have to keep in mind. See, monopropellant rockets are very versatile. In fact, I think I should tell you this example. H2O2 I did not consider, I always kept in terms of hydrazine. Why is it? Can somebody tell me? All I will tell you, give a clue, is N2H4 hydrazine has a standard heat of formation of, we said, something like plus 50.3. When I talk of hydrogen peroxide, the standard heat of formation, I have to put a standard here, is equal to something like minus something like 187 or something kilojoules per mole, kilojoule per mole. Therefore, now somebody can tell me why is it that hydrogen peroxide is not used much as a monopropellant. The standard heat of formation is terribly negative. It again forms something like H2O plus O2, and these are 0. That means the amount of heat which I can generate is, the heat liberated is going to be very much smaller, because here I have positive, and therefore I can get this coming out and giving me heat. Therefore, the temperature what I can get by H2O2 decomposition will be very much smaller, and therefore universally, if we see, other than maybe in early part of the program, maybe in 1940s and 50s, we used hydrogen peroxide as monopropellant. Nowadays it is not being used at all. The reason being, I get extremely poor performance. And why do I get performance? Because this heat of formation is much more negative, and these things we have covered earlier. But there is one application. In fact, whenever these Olympic games occur, you would have seen some people having in their belt something like a rocket, and they go across, like in Los Angeles Olympics, you find human beings being propelled in the sky using rockets. And what is it? For human beings to fly is very difficult, because we are all aerodynamically terribly unstable. for something to fly you need a good configuration, you need an aerodynamic configuration which can fly. We have hands and legs and it is not possible, but I can always have a belt, and the hydrogen peroxide which is used is known as a belt rocket. You know, all what is done is you have a stabilizing device, like let us say a human being, I plot like this, hands, legs is like this. You put a stabilizing device on him, maybe make him little more aerodynamics, and maybe put a small monopropellant rocket over here, and he, whenever he want, he switches on a rocket and he can go in different directions, and such type of skydiving or acrobatics is done during some of these carnivals like Olympics and all that. And I give a problem on this belt rocket. Now something which I think I must tell something, since we are talking of propulsion in the master's degree program. See, you know, monopropellant rockets can give extremely small impulses. What do you mean by small impulses? Maybe if I say the change of momentum is impulse, delta mv is equal to impulse I can just pass a small amount of hydrazine and it gives me a small value of Vj. The Vj is much smaller than a bipropellant, and therefore I can get very small amounts of impulses. Why are impulses important? Supposing I have, let us say I used I showed you the case of a INSAT spacecraft. I have something like 16 rockets at the edges of it which are there, and which we say, you know, I generate small amount of thrust such that if its axis is not in proper shape to be able to correct it and all that, which means I have to supply a small impulse. How do I supply? I need a very small amount of propellant to go and maybe make a change in momentum. Now it is very useful for small corrections, but I also know that I would like to have higher value of specific impulse when, if I want to power it, if I want to take a satellite from one orbit to the other, I need to supply steady value, I need a larger value of ISP. Therefore the question is, can I use hydrazine N2H4 for both in the bipropellant mode as well as in a monopropellant mode? What is it I am telling? Let us again think in terms of a configuration. Well, I have the hydrazine tank, as it were, tank of hydrazine. I allow it to come to through a maybe a pressure regulator over here to a series of small rockets which are all monopropellant rockets, all have catalyst in them which can be used for small maneuvers. And I also carry, let us say, MON3. You all will remember MON3 is something like N2O4, in which I add some amount of NO such that it has a lower freezing point, and I also take little bit of this here, I take this here, I also give this to a slightly bigger engine or rocket engine, and when I want to change the trajectory I operate it with hydrazine and MON3, let us say, or mixed oxides of nitrogen, generate a thrust. When I want small corrections I use this, and this is known as a unified propulsion. Of late I do not see the word unified being used, they say it is a dual mode propulsion. What dual mode propulsion means? Hydrazine is used as a bipropellant in part of it, and part of the system it is used as a series of monopropellant rockets. Well, this is the dual mode propulsion, but something, even solids can give small impulses, and this they are doing at this, they have reported at JPL, wherein you have maybe on a silicon wafer or something, you have small pellets, micrograms of solid pellets, and you have a resistor wire incorporated in them. Whenever you want a thrust, you want this thrust in this direction, you press a pellet in this direction, you have a small force going, and this is known as digital propulsion. As you see, you know, the subject of propulsion, especially rocket propulsion, is something in which a lot of developments can take place. All what I want is, I want a spacecraft to be given some small force like this, it is in vacuum. Therefore, I have a pellet here which I fire and it gives me this. If I want a pressure in this direction, maybe I put some string over here, some pellets here, I fire it in this direction. Therefore, this is known as, you have something like digits which you fire, it is known as digital propulsion. But what is conventionally used is maybe something like a combination of these things, but hydrazine with MON3 creates combustion problems, which I think I will address when I get into combustion instability problems. Well, this is all about monopropellant rockets. Just to summarize, we have cold gas which gives extremely low performance, monopropellant which is still low, which is somewhat higher, bipropellant which is quite high. And as I told you, in a bipropellant mode, it gives a hydrazine with N2O4 gives much higher performance than with MMH, and therefore it is desirable. Japanese people make use of these things, but I think we still have to understand a little more about it. I think this is all about monopropellant rockets, but just to complete the subject of rockets, we can also have, instead of monopropellant, bipropellant, we could have 3 propellants, tripropellant rockets. What are tripropellant rockets? Maybe I have something like kerosene, I have liquid oxygen which can be used as boosters. I also carry maybe liquid hydrogen, and what happens when initially when I burn the system, I start burning kerosene and liquid oxygen together, and into this I can also add little bit of liquid hydrogen which stabilizes the combustion. And when the booster stage is over, into the same chamber, now I cut off the kerosene and use these 2 propellants, and this becomes a tripropellant rocket. The advantage of a tripropellant rocket is a single rocket can be made to go to space. Well, it has still not been used, but there is some interest in having the tripropellant rockets. I think I should stop here, but before stopping, as usual, I think we have not done anything about hybrid propellants, right? Before I start the next lecture on combustion instability, maybe I will spend a couple of minutes on hybrid rockets, because I find it has not been very promising earlier, but of late some private people, like the millionaire by name Bert Rutan, he formed a company known as Scaled Composites, and he used hybrid rockets for ferrying people to space. Maybe he says space can be used for enthusiasts who are interested in looking. Therefore, he says it is something like a voyage or something like a place where you can go and view the earth from top, and therefore he used that an aircraft known as White Knight. He has some hybrid rockets and the space capsule in this. This aircraft takes him to a height of 14 kilometers. From there he takes the tourists into space and into a suborbital flight and makes them come back over here. Maybe we will spend some 5 minutes on hybrid rockets in the next class, and then get into the question of combustion instability, right. Well, thank you then.